Fascinating. And since there are no further questions, let me introduce to you our next speaker, and that's Petr Potapov. Petr has several courses. Petr works at the University of Maryland, USA, and he's going to discuss application of analysis radio Landsat data time series for land cover mapping and monitoring. Petr? Yes, can you hear us? Can you please stop sharing your screen so that Petr can share his screen? Off.
And we cannot hear you.
Мы вас хорошо слышим, Петр, и видим. Сейчас мы, значит, секундочку. Да, теперь мы видим вашу презентацию.
Окей, good. Прежде всего, я хотел поблагодарить.
All right, then first of all, I would like to thank the organizers for inviting me to speak at this very interesting conference, and I will talk about our lab. We are the Global Land Analysis and Discover Lab. We are known as GLAD for short. And we are associated with the Department of Geographical Studies of the University of Maryland. Most of our work has a very wide geographic coverage. Usually we're talking global or international or continental coverage. And the changes that we are monitoring usually occur over decades, if not centuries. Just to give you an example, together with the Institute of Forest Resources, we produced, together with the Global Forest Watch, we produced maps that we update every year that show you tree canopy cover and forest cover change. There is another product which is updated daily and which focuses on tropical forest. And Amy Pickens, our PhD student, last year published another product which shows water bodies, lakes and rivers changes globally in the last 20 years with this temporal resolution of 1 month. This data is also available at our website and as assets in Google Earth Engine. Today I will present a product that we produced just recently. We are combining optical data and the JEDI LIDAR data. All the products that we are making are in the public domain, and I ask you to click on these links. Again, you can find our products not only at our own website, but you can also go to Global Forest Watch, their websites. Most of our products are also available via Google Earth Engine, and some of our products are also distributed as quick map services, and they're available at QGIS using the QMS extension. Since we operate wide-scale geographies and extremely long time series, Landsat data for us are critical, and our lab can store a complete archive of Landsat data from 1997. It's updated automatically every day, and we also generated a system of automatic processing of the data and converting them into data for analysis. They are the so-called analysis ready data, ARD. And the first step in the process is to analyze the quality of the image per pixel. We use our own models of quality assurance, and we use other people's techniques, but we believe that our method shows not only the clouds and their shadows, but also it identifies topographic shadows, and we can separate land, water, snow, and ice under clear skies. Usually, this layer is used to process Landsat data, but some of its components are independent means, such as the water mask that can be applied onto every image if you want to understand the dynamics of the surface area of a water body. The next stage is radiometric correction. Usually, we use data without correcting for the atmospheric interference. We use the MODIS data that shows the surface reflectance for normalization of data, and this normalization happens automatically. We identify, we define the objects that we consider to be stable or permanent, where we see the same land cover in the same condition, in the same status, both on MODIS and Landsat, and we compute the difference in reflectance, and we take it to be a function of the angle of imaging. So in one model, we can adjust for scattering and of light and absorption of light by the atmosphere, and also the anisotropic effects of the albedo. After that, we aggregate normalized data into 16-day composites using the images with the best quality. The 16-day interval is selected in view of the Landsat cycle, and it also matches the most popular MODIS format. This data is then converted into geographical coordinates. They are stored with a 27-meter scale, and we can quickly select regions for regional and local projects, and we can also do parallel computing with them. The main properties of the data that enable us to do our work is consistency in spatial and temporal properties. Spatial consistency enables us to extrapolate our classification models or the vegetation structure models to wider areas. And I wanted to stress once again that correcting for anisotropy is critical, because otherwise the data will not be extrapolatable, and we would have to retrain the model for every image. Temporal consistency is even more important. It allows us to identify changes in the land cover, and we can also use phenological characteristics. To the right, you can see a time series of 32 years for a pilot site in for a test plot in Laos, Laos. And here you can see the red and the near infrared and shortwave infrared comparisons. The image show you the cloudless composite images for the last 30 years. And this is how we can interpret with a high degree of confidence the changes in land use and land cover for that pixel. We see that at first it was a natural forest, which was disturbed several times due to cleaning of adjacent territories. In 2004, this part was also cleaned, and then the crowns of the trees were restored, but the phenology changed. We see that this type of trees, this species, in the dry season, they shed leaves over a short period of time. We know that in Laos, they are today expanding the planting of rubber trees of the heavier. So we can see both what was happening in a particular area and how it happened, what the results were. we do not use 16-day composites. Instead, we use multi-temporal metrics to analyze phenology. Over here, you can see the distribution of reflectance during the year, the values of the indices, and also the dynamics of those indices during the year. We use more than 100 different metrics. Each of them is associated with some unique feature of the land cover. Some examples are given on the right. These are the color composites of the metrics for the Mekong River Delta in Vietnam. You can see that different metrics show you different types of land cover, and we can separate aquaculture, the ponds that are used to cultivate shrimp and fish, from agriculture, which can be differentiated from urban areas, which can be differentiated from gardens, which in that turn can be differentiated from rice pads, and we can even understand the difference between rice plantations and yams plantations. Here is our cooperation with NASA Survey. We did another program together with them for the Mekong River. This software is available on the website. It's updated once a year, and in the system we used LIDAR data to produce a model and to calibrate the model that is applied to annual Landsat phenological metrics, and we can see the cover, the height, and several other parameters. And if you combine these metrics, you'll be able to produce maps of forests using the forest class criteria and referring to different minimum height and minimum closure parameters to classify your forests. These are some results that can be obtained by the users for every country, for every region. You can see the difference in forest area. You can see the changes in the forest regeneration, the net area of forests, the ages, the forest age in 2018. You can see that more than quarter of forests in Vietnam were younger than 17 years. And we also have data for primary forest areas until the year 2000. You can monitor the changes. And this is very useful in various environmental protection projects. Another set of metrics that we're using are related to change detection. Here we take a different approach. We look at the differences in every 16-day interval in the reflectance between the current year and the previous year. So you take the time series of the differences, and based on that, we generate metrics. They help us find areas that changed in the last year. An example is given on the right bottom image is a color composite. Blue is area with no change, and red is change that, well, in this particular case, that happened in the last 4 years, not just 1 year. We can also efficiently find areas where forest was felled and where forest was partially damaged as a result of windstorms or fires, under the canopy fires. We can see here circles that are very typical. They are like the circles on water that show the daily cycle of a fire. Fires burn more intensively during the day and less intensively at night. To the right, you can see selective felling, and our metrics show nicely the structure of this logging and well the transportation sites were organized, and the rest of it. We have products that we update every year and that show you changes and disturbances in the forest. Again, you can find all these products via Forest Watch and Google's engine. This is our most recent product based on GEDI, the Global Ecosystem Dynamics Investigation satellite, which was launched in 2018. And from April 2018, it's been collecting data. The data is processed by NASA, and they publish the data with a big delay. Until now, we have only data processed between April and November 2019, and we use two products of the second level that show the characteristics of reflected energy, which can be interpreted as properties of the tree crown structure. The map shows the points scanned by the device itself, by the scanner. Every footprint has a diameter of about 25 meters. The relative height metrics themselves are not an indicator of actual stock height. We used aircraft images done by a LiDAR. In order to arrive at more accurate estimates, the aircraft LiDAR data has to be converted from high resolution to the satellite resolution. We're using the 20th percentile of the altitude in order to cut off the highest points in the clouds that are most likely the tool error. The 19th percentile inside the 30-meter pixel of the aircraft LiDAR, we consider it to be the height of the crown. We compare it with various RH metrics of GEDI. We find out that 95 RH has the best correlation, RH has the best correlation with the aircraft data, but the data is still not perfect. They show us very big heights, altitudes, in the middle of the Arabian Desert or in the fields in the Alps, where definitely there are no high trees, and they do not also distinguish electricity lines or high buildings from forests. So we had to apply additional filters to detect correct data to train our model. The data is also very uneven. Since this is an infrared LiDAR, it cannot scan through the clouds, and in the cloudy areas in the tropical regions, we have very little data compared to temperate region forests. There we have a lot of data. We built our model so that it would be global, and since this is an empirical model, we wanted to be able to process local forest structures. That's why we produced regression trees-based machine learning models for every plot of 1 by 1 degree. So more than 11,000 models, almost 12,000 models. So calibration data was collected from 12-degree radius around each target tile, thus providing us with a stable distribution of forest heights around the world and ensuring high accuracy at the local level. Here you can see an example of the map. The differences in heights in stock that are attributable to the conditions of growing, the type of forest use, etc. This map validation yields good positive results. At the same time, it uncovers one of its major deficiencies. This model is not capable of assessing correctly the height of a tree that is, or a forest that is higher than 30 meters due to limitations of Landsat, and also due to the noise in the LIDAR and JEDI data. We are going to polish our model. We note that other researchers obtained better results for high trees based on textural metrics. But for practical use, our data is workable. In this table, you can see the accuracy of forest maps that are produced using various height accuracy criteria. And we are comparing that to the JEDI validation data and the aircraft LIDAR data. We can also use this model in time, and we can apply it to different years. The map you're looking at is from 2019, but we can reproduce it for the year 2000 or 2010, and we can get RGVs for these two time points. You can see on these composites the different types of changes in the forests. It's not just deforestation or forest regeneration, but you can also see high forest rotation, like in Arkansas or in Malaysia. And the most interesting bit, all generated data, the pre-processed Landsat data is, like I said, in the public domain. We have a very simple API. You have to register the website, you have to get an account and a password, it will never expire. And then using very simple commands in Carol or G4W, Perl, you can download any part of the data for any part of the world for any time period that we make available. At the moment, we have 1.5 petabyte of global data. We are testing the new version of the tool, version 1.1. This version will be completely open source. And of course, it is also available for free and open use, and it will include not only the tools to obtain metrics, but it will also have inbuilt machine learning tools to classify, to assess changes, and for interpretation. This is how you can treat this data. Recently, there was a similar workshop in Vietnam, and this is the slide that we used there. We download ARD data, we create multi-temporal metrics, then using machine learning, we produce maps for every topic or every class of land cover. We combine these maps using an image modeler that is part of this solution, and these maps can be produced for different years, so we can produce a time series of land cover. And as Dmitry mentioned in his talk, in the reports, especially if it's some international report, like, I don't know, a report on like UNFCCC, the carbon emissions report, we need to use statistical samples to assess the area with a known error. And we need to know the accuracy of our map. Our system allows you to select points using stratified random sampling. And you can also create visualization of Landsat data bi-monthly, biannually, or that is to say, annually, and you can link this to Google engine, the Google Earth. This is a paper that we published quite a while ago. We cooperated with the Forestry Department of Bangladesh, where we used our metrics to map forests and changes inside the country. We use stratified sampling to analyze changes of the tree cover, not only at the level of the Landsat pixel, but we also used high resolution, super high resolution data. And the Forestry Department of Bangladesh used these inputs to analyze changes in different kinds of forests and also to make reports on carbon emissions. And the last slide in the presentation, I hope that the presentation will be available somewhere on the presentation website. That's why I'm leaving the links here on the slide. Some time ago, there was a conference, another conference, where we published not only the GLAD 1.1 for beta testing, but there is also a manual in Russian, which explains how to download the data, how to create metrics, how to work with machine learning, how to classify, and how to analyze statistical samples. And we are using examples from the north of the Moscow region. We are telling the reader what can be done in order to improve the accuracy. You can look also at the damaged area by year or by type of the damage, which is not always possible to do using Landsat. So that's these are all the data that you can retrieve, that you can analyze using our system. Thank you. I'm done. Piotr, thank you so much. Yet another amazing presentation. Every time we'll learn something new from you. I'm sure that many people in our audience are already your users. They are using your products. And it's always nice to get, all the latest news from the horse's mouth. Let me see if we have any questions in the chat. There were several questions. Did you see? Did you see the questions?
Да, значит.
Okay. I can't read very well. I can see that there are a lot of comments. Thank you very much, Piotr, for your work. Thanks for your products. Okay, this is a thank you. A question. The start of the season value, how do you define this? Or how do you compute this metric? I think I have it in the paper that we've published in February this year. If not, then I will include this information onto the website. We're using the curve of change. Okay, start again. All seasonal values are based on the radiation index, and we look at the vegetation index, vegetation index. We'll look at the first 16-day interval where the vegetation index starts growing, where it starts increasing. So we're always looking at the start of the vegetation index growth. It is not a very accurate value because we do not have every 16-day interval for every year because of the clouds, and it means that it can be shifting the position. The Landsat data is not MODIS data. We do not have everyday imaging, and sometimes 16-day intervals can be left without data. Okay, I understand that. Which technique for atmospheric correction do you use for Landsat data starting from late 80s until now? Does it enable compatibility? Can we compare the metrics from different time periods? We use stable data that we received analyzing MODIS data for the past 15 years. Stable data of reflectance coefficient. Our data set that we use for normalization does not change. Maybe in the future, when there is version 2, correction 2, we will change that approach and we will use data with surface reflectance that USGS will provide as a standard product starting from the second release. But right now we are operating standard MODIS data. That means that the data that Landsat captured, the data that appeared before the year 2000 can still be compared with MODIS data that are dated after 2000. We identify automatically the pixels, the area on the image, where we assume that the land cover and its phenology is the same between Landsat and MODIS. And we can almost always find a relevant site, a comparable site for MODIS. As to atmospheric correction and calculating a true reflectance using the transference model, we don't do this. We use normalization. Our system was developed even before release 1, correction 1. We are thinking about surface reflectance model once it has come out, and we expect this to happen together with the second release correction to early next year. Why didn't you use ICESat-2 data for boreal forests where there is no JEDI cover? Oh, this is an excellent question. We have a PhD student who is also a co-author of the article that we're going to publish. And that PhD student is doing exactly that. We compared ICESat-2 and JEDI metrics, and we see that they are not fully matching. So we had to find a set of metrics that would show us the same value for JEDI and ICESat-2. The first version of her map, of that PhD student's map, shows us better the height of sparse forests. We don't have JEDI data for certain latitudes. They're limited by the 52nd latitude. So in the future, that maybe we will release an updated version of the map where we'll be using airborne data, all the data that we have for the world, and JEDI data and ICESat-2 data for calibration of the model. Thanks. Thank you. Since this is the last presentation and there are still questions, the second question is, surface reflectance of by USGS and Landsat calibrated according to your methodology, are they basically the same or there are some differences? Okay, I'm going to find a slide where I'm comparing our data, left bottom. This is normalized surface reflectance. This is what we produce for Landsat, and MODIS corrected surface reflectance for the same dates, for the same 16-date composites inside the US. There is a good matching between, good agreement between these two sets. One of the goals of our product is to create a stable product that can be used to extrapolate models of classification or regression analysis of the vegetation structure. We were not interested in obtaining precise data that would be showing us surface reflectance exactly at the point of the survey, at that time, exactly at that time. I know that there are other projects where you might need that kind of data. For instance, if you are analyzing the productivity of crops. So in the future, We are thinking that maybe we should integrate surface reflectance as well. But the problem is, if you start reading any article that are using any surface reflectance correction 1 products, and they're using extrapolation of the classification or regression model to large areas, you will find that the author normalized this data, because without normalization, the model would not be extrapolatable outside of one image. We don't know how it's going to work yet, and whether we will need an additional normalization of data. There is good probability that yes, we will need more normalization and extra normalization. Okay, thank you very much. Another question. The calibration. Oh, no, we read this question already. Okay, another question is in English. Very interesting. I am particularly excited by the API for access to and integrating the data into applied conservation projects. Thank you for implementing that. It's not a question, it's a comment. It's a thank you. Many possible applications, very interesting. Thank you again. Another thank you, Piotr, and thank you. And I think there are no further questions. I don't know, maybe we have more questions from the floor. Well, anyway, Piotr, thank you very much.